So welcome everybody to Pathways in Nuclear Engineering. So before we introduce our fabulous panel today, I just want to go over some details about CEE. I know many of you might have found out about CEE through the internet or through Google searching. So CEE, or the Center for Excellence in Education, was founded in 1983 by Joanne DeGennaro and the late Admiral H.G. Rickover, who's the father of the nuclear navy and civilian uses for nuclear power. Our mission here at CEE is to nurture high school and university scholars to careers in excellence and leadership in science, technology, engineering, and mathematics, or STEM, and to encourage international collaboration between and among leaders in the global community. At CEE, we have four fabulous programs as of right now, the first of which is RSI, the Research Science Institute. RSI is a highly competitive 6-week summer science and engineering program open to rising high school seniors. Juniors are eligible to apply. We have just closed our session of RSI last week. We had a fabulous closing ceremony. So congratulations to any of our alums that could be in. RSI is the first cost-free summer science and engineering program that combines on-campus coursework in scientific theory with off-campus work in science and technology research. Paired with RSI, CEE is also responsible for the USA Biolympiad, the premier U.S. biology education and testing program for high school students. U.S. Biolympiad provides the motivation, curricular resources, and skills training to take students beyond their classroom experience to the level of international competitiveness. Since CEE began administering the USABO in 2003, every member of the USA Biolympiad team has medaled at the IBO. And we have just closed that session in Quezon City, Philippines for the International IBO. Congratulations to the winners, the gold medalists from the US Biolympiad team. Woohoo! Next, we have the Teacher Enrichment Program, or TEP. TEP provides opportunities for middle and high school teachers to connect with leading experts from industry and academia, explore cutting-edge research and development, and make meaningful professional links with direct benefits for teachers and students. Finally, you have our program, which you are present to right now, which is STEM Lyceums. STEM Lyceums is a virtual club for high school students to meet once a month to learn about STEM career pathways from leading field experts or to learn general soft skills for college, like resume building or recommendation resources. We talk with industry professionals to share cutting edge research and offer unique learning experiences like scholarships, internship opportunities for high achievers. We also provide resources for students that are particularly active in the club, like the STEM Lyceums Mentorship Program, where we pair students with alums from RSI or USABO to learn more about a specific pathway that they might be interested in, or to receive advice or research resources as they transition into college. So these are all things that STEM Lyceums does, cost-free to you all. Before we go into the introductions, I want to quickly go over some Zoom norms. So if it's your first time here, what you do is you place your questions that you might have in the Q&A function. As the moderator, I will go through them, generally put questions into certain categories. So if you have a question but you haven't heard it been answered yet, just be patient. I have it sorted and organized in a specific way. I'll get to them. I'm very good about that. So please wait until the end of the session for your questions to be heard. I will select and share the questions in a timely manner, and we'll just keep the flow of the conversation going. If your question for some reason is not answered in the session, like if we run out of time because we have such good discourse going, I send them at the end of the session to our panelists so that they may answer them in email form, and then we include it in our newsletter. If you're not subscribed to our newsletter, please fill out the student interest survey on the CEE website. And again, yes, a recording of our sessions will be provided to you once they're ready and edited to perfection. All right, so now I'm going to go into our introductions. I mentioned this before, but we have some great Virginia Tech representation happening today, so I'm so excited to introduce our two speakers today, first of which is Sharon Smoot. So Sharon most recently was the president of BWX Technologies Nuclear Operations Group, overseeing the operations providing a complete range of nuclear components and services for the U.S. Navy. She was the leader of marketing, strategic planning, and business development for Bechtel's Nuclear Security and Environmental Global Business Unit. She retired from the U.S. Navy Senior Executive Service, SES, at Naval Sea Systems Command in Washington, D.C. as the Vice Director of the Navy Staff in the Office of the Chief of Naval Operations. In her 33-year Navy career, she led 10 commands, operated 4 naval shipyards, and oversaw the execution of all Navy shipbuilding contracts, SUPShips, and led a Navy staff of 400 flag officers and senior executives. Sharon is the recipient of numerous awards from the Department of the Navy, Black Engineer of the Year Award, and Presidential Rank Award. Sharon was presented with the 2023 Virginia Black Business Leaders Award. She is a career nuclear engineer with a bachelor's degree in electrical engineering from Virginia Tech and a master's degree in engineering management from Old Dominion University, or ODU. She holds professional memberships in Society of Women Engineers, National Society for Black Engineers, and the U.S. Navy. Moving on. Our next panelist is Caleb Barnes. So Caleb Barnes is an Associate Director for Fusion at the Special Competitive Studies Project. He works on the Commission on Scaling of Fusion Energy, which is co-chaired by 2 sitting U.S. senators. Prior to joining SCSP, he worked in the Virginia Tech Transport Theory Group, VT3G, developing machine learning programs to predict the location and amount of burnup in spent fuel casks. He holds a master's in engineering in nuclear energy engineering from Virginia Tech and a bachelor's of science in physics from the University of Virginia. Thank you two for joining us. So we're going to start off by passing this over to Sharon to start us off, and then we'll hear from Caleb.
Thank you very much. I will pull up my slides while I'm doing that. I'll just say go Hokies. It's our day. So Rebecca went through most of my background. The only thing I would add to that, and hello to all the students online, is that I'm also a trustee on the board for the Center of Excellence in Education. So I'm very biased towards our program. So I'm happy to have all of our STEM Lyceums online today, and maybe some of the alumni from some of our other programs. It is a really treasured program for each of you to be participating in. So I'm so happy you're here. A little bit more about what I have done in my career, and then I'm going to back it up to what how it all started for me in high school and go for it from there. I worked in naval shipyards, but I started my career in industry, so 33 years and some months with the federal workforce and 8 years with industry, some before I joined the federal government and some following my retirement from the federal government, but always associated with the Navy nuclear program. So CE became a defining moment for me because I have always worked in my adult career in something associated with Admiral Rickover's program, and with people who knew him personally. While I didn't get to meet the late Hyman G. Rickover, I did get one time to meet his wife. And so I will treasure those times and all the lessons learned that I got from that part of the program. CE wasn't there when I was in your grades and I'm in my earlier academic program, but oh my gosh, I wish it was. So bachelor's degree, master's degree, all things I would encourage all of you to also pursue as you finish your grade school academic career. I will share just a short story with you before I go on to the next slide. I did a co-op program, and I'll talk to you a little bit about what that is and how it benefited me at Virginia Tech. Once I completed that program, I had every intention of going back to the company I was working for that was in the area of naval nuclear power. At that time, and then in that particular year that I was graduating from college, they had a limitation on what women could do relative to radiation exposure, meaning I couldn't get any. And for an entry engineer going into a program that was a nuclear program, which meant all of my components were in the reactor plant, it was a little career limiting for me to not be able to go into the plant ever. You don't go in when it's operational, obviously. But I then transitioned over to federal government to then Norfolk Naval Shipyard, and I was able to hit the ground running there and enjoyed every minute of my career. And I wish that for each of you as you complete this part of your academic career, you move forward. And I hope all of you land in a career that you actually love. So with that, I'll start with my education. So my journey began in grade school. I will tell you even earlier than that, I was the kid that liked to take things apart and I sometimes could put it back together again. My dad was in an electrical technical career field with the United States Air Force, so I got it from him. And I was just curious on how things worked. And so I took that into my high school career. And I had a little bit of a different type of academic career because I was an Air Force brat. I actually went to 22 different schools and I lived in multiple countries. So I did most of my early years in Europe and my later academic part of middle school and all of high school in the US. So I'm a mixed bag and a little bit unique type of person as I came up through grade school. But it was when I got into the 11th grade, I had a math teacher that was, his name was Mr. Wallace, that was an engineer. And he was an excellent teacher. He was the one that got me interested in engineering and explained to a number of us who were also interested in engineering what it actually was. He took us under his arm and kind of nurtured us in some of the classes that we took. He even did summer programs for us to get us ready for some of the freshman year college of engineering classes that we had to take that weren't being taught in the high school that we were in at that time. So he was the one to propel me in the direction to go major in engineering. I was bouncing between pre-med and engineering. And when you do those wonderful tests, I don't know if they do those anymore, that says, here's what you're going to be when you grow up. Everything pointed toward medicine, which I love that too. But engineering grabbed my heart, and I'm glad I went with that. And I credit a lot of that again to my math teacher. As I went through high school, as you're doing, I took the advanced placement courses. They called them something else then, but they were all the accelerate courses, but only in math and science because that's what I loved. I probably should have done English too, because writing is a skill that we all need to have and master, and I found that out later. I did okay with it, but I could have pushed myself a little bit more. But I loved the sciences, all of the sciences, and in particular physics, which also helped with electrical engineering, and math, as much math as I could take. I also took summer programs, whether they were with my high school or any local community colleges. And then I would also tell you that there are plenty of opportunities for you to take college credit courses. You have to look at your community colleges in your local areas, but other than placing out with your AP exams, there are other opportunities over the summer to also take some of those entry level, those freshman year standard classes and get them out of the way if you have time for those. And then, of course, as Rebecca said in our opening, we have these wonderful programs, and I highlight the one that is my favorite, CEE's RSI program, which is a highly competitive program. And I hope you all would, some of you who have been in that course, if you in that program, if not, I hope some of you will apply to. It's very competitive, but it's very rewarding. There are a large number of programs that many universities offer. MIT does this one, and there are very few who offer them at no expense to you or to your parents. And then there are just a number of summer internships that hopefully your high schools are providing you information on that could offer volunteer opportunities shadowing opportunities, anything that gives you an opportunity to see what that career field actually looks like. Then when I went to college, I ended up going to Virginia Tech. I ended up having a MITES program that they had there that exposed me to their engineering program. I chose Virginia Tech over the other three that I applied to and was accepted to because they gave me more scholarship money. That's what it came down to, is they paid for me to go to school. I also applied my freshman year to their co-op program, which adds an additional year. So you're in a 5-year program, which I thought was fabulous because I wasn't ready to do all the adulting that happens after you graduate from college. So I graduated high school at 17 and I still wanted to learn and have fun. And there were some internship opportunities on campus. Another thing that I did, there are a number of grants that most universities do within their College of Engineering in particular. And I did sit on the College of Engineering board for 2 or 3 years at Virginia Tech. So I learned a lot about this, how our professors in these colleges of engineering across all the universities have grant programs. And those programs offered opportunities for undergraduates and graduate students to continue doing studies and research and things of that nature. And I was able to do that one summer, and it was just fabulous working with the professor that was leading a particular study and knowing that I contributed to something that is commonplace, at least at Virginia Tech, that as that technology evolved is now commonplace today. But 4 decades plus ago, it was not. So that tells you how old I am. And then graduate school. I was one that after coming out of college for 5 years plus a summer, because I did that grant program over the summer, that I needed a break. My son didn't do a break. He went straight through undergraduate to graduate. I would encourage you, if you're going to go into any of those STEM career fields, go ahead and pursue your master's. And depending on what you want to do, and you've got plenty of time to think about what that is, you may or may not choose to go for it with a PhD. Because I knew I was going to go into a program associated with what I was doing in my co-op program with, whether it was with industry or with Navy at the time, I did not at that time pursue a PhD at ODU, and they were pushing me to do it because I knew I was not going to, at that time, was not going to go into research or to the laboratories. If you have an affinity for research and laboratory work and design work, then I would encourage you to consider that in your academic career as well. And there are plenty of great professors and people and mentors and other students out there to help you navigate through that. Here's some of those programs that I mentioned. So you've got plenty of camps and internships, some that have paid, most that don't for high schools. But a lot of the Ivy League schools offer programs. They're all online and available for you to look at in every area of STEM that you can imagine. So Introduction to Engineering up at the top, Technology and Engineering is one of the programs I went to. And we talked about Research Science Institute. There's a Summer Academy for Math and Science at Carnegie Mellon. There are a lot of pre-college programs at a number of universities like Harvard, University of Pennsylvania, UVA, Carnegie Mellon. There are just a host of them. I would take the time now at whatever grade you're in to go online and start looking at those programs. The ones that cost money can run anywhere from $500-600 up to $9,000 and $10,000. And so it's important for you to think through that and talk with your parents about what those possibilities are, but really look at what those programs offer to see if anything that they're doing really resonates with you. And the feedback I give you about these programs is anytime you can get an exposure, whether you're in high school or in college, to a particular career for so you can see what those words actually mean in reality, it will help shape where you go through high school and college relative to what your focus is on a major later or a career. And it also offers opportunities for you to have mentors, which I had quite a few of before they were actually called mentors. People who would just kind of nudge me left or right or give me feedback on, hey, this you're really, really good at this. You should try it. And because they were people that I trusted, I did. And some of those things were not for me, but there were a lot of them that I just fell in love with. And that helped me throughout my career. So 42 plus years later, I am finally retired, sort of. I do a lot of things like this for middle school kids and high school kids to encourage our kids to go into STEM and to excel, and just there for them as advisors, mentors, or anything that I can do to give back. So in my career, I left college. I went to work for the Navy. The Navy paid for my master's degree. I started off as a junior engineer, but a junior engineer that had 2 solid years of experience, which was a plus for me. So I got to be hired at a higher level and given a little more responsibility because of the work I had done while I was in college. But it was really more technical support. That's where I learned how to do technical writing, which we did not do in college at my time. That then shifted into research and design work. So anytime, any opportunities you have to do research work or look laboratory work or anything like that in your high school career and certainly in your collegiate career, please look at that and try it. And the other tool that I got coming in my first, I'll say first 10 years is project management. Learning how to do team building, learning how to develop a project, getting certified in different parts of project management in order to execute the work, whatever the work is. And for me, it was certain systems on board Navy ships. With that came promotions and jobs that with increasing responsibility, and all of a sudden I became a supervisor and then a manager, and then you become responsible not just for the project but for leading your team, building a team, leading the team. And so I spent the time to learn how to be a good leader. And I would tell you that I still have not perfected that, but I focus a lot on that. I train people on that. I share my stories with those that are in similar career fields of things that I did well and things that I didn't do well. But leading people is a skill set that I will tell you I did not get out of all of my collegiate, all of the degrees and certifications that I got. It's what I got out of intentional study and what motivates people, what grabs their heart, how I grab their energy, and how I best support them. And I'm so glad I spent that time in that half of my career learning how to appreciate people, because it helped me tremendously when I got into the executive level team, which is for the federal government, a senior executive. For industry, it's called the C-suite, where you're leading quite a few people. And so the numbers of people that I led at the peak of my Navy career with 10 different commands, I had 45,000 civilians across the world. I had about 1,500 military officers. And on my staff in my office, it was a little over 200 people. So think of the size of that team. It is very much dependent on the person at the top of that pyramid having really good leadership skills. And so I continued to work on that, and that's the executive leadership piece. What also comes at that level, and this is the back end of my career, is understanding the business acumen. My core is technical. That's where my passion is in engineering. And that's where I will dive into and stay if you let me. I had to pull up with help from my master's degree and learn the business side of every industry. Every industry, any industry you pick, will have a business side. In order for that company or that agency to operate, there's always going to be a budget. There are going to be personnel and personnel matters. There's all of those elements of business. And so at the appropriate time, you'll need to open up your aperture to pull that piece in as well. I will tell you, in my graduate school, accounting was the one thing that almost did me in. I like to program automated solutions for things, and accounting makes you do everything by hand. It drove me crazy. Change management was something I did later towards the end of my career, and shifting directions, whether it's a strategy or through the administration or just through the CEO saying, I want to do something different. I want to get into something different. And then partnerships and coalitions. The higher up in any of the companies or federal government I went in, the more important partnerships and coalitions became, whether they were with colleagues that were at the same level, different agencies that I worked across, all of the military services that I coordinated across, or just partnerships between companies like the technology of fusion or any other technology. I worked a lot under with some of the DOE programs where you have companies that are competing for the same thing or partnering together for the same thing. The same thing meaning end in mind to win a contract to go develop something, to go construct something, or just to make something happen. And that's a skill set that I learned probably later in my career than I should have, but I would tell you, focus on where you are now, learning as much as you can, exploring those options. And then as you progress through your academic career and then your professional career, build on these type of skill sets. Now, my engineering career field, this is specific to me, and the challenges that I faced as a supervisor all the way up through executive leadership is finding the talent that we needed, whether it was with the federal government or with the or with industry, finding that talent and retaining that talent, and engaging with universities to ensure that they were teaching the classes and things that we needed in order for those students who were graduating to have the skill sets that we needed them to have in order to meet the challenges, which were largely not just maintaining the technology we have now, but developing that new technology. The acceleration of technology or technical evolution was slow in my day. It needs to move much faster as cell phones have evolved. The technology of the next nuclear power thing, whether it's fusion technology, which I'm super excited about, or just different types of fission technology like the small modular reactors, different types, exploring different types of coolants and things that make that clean energy option more viable, more affordable, things of that nature. So the most exciting thing to me is what AI brings to the table. Machine learning, 3D, 4D, virtual printing. I mean, all of these capabilities were things that I worked on, but AI is the game changer. And whatever follows AI is going to just blow my mind. But what we can do with it today is going to be nothing compared to what we do with it tomorrow. You are the ones that are going to bring tomorrow's solution to the table. So I can't wait to just see how you guys navigate this space. And so I will end there because I think I was supposed, hopefully I didn't go over my time. And I know we're going to save questions for later. So hopefully I covered everything I was supposed to cover, Rebecca, and I will turn over to you and to Caleb.
Thank you so much, Sharon. That was fascinating. I love that intersection between what we are doing in industry and with the military and how all of that is coming together to advance the sciences that we're working on. So I'm going to go ahead and turn it over to Caleb.
Hi, everybody. So first off, I want to say what an honor it is to be able to share a stage like this with Sharon Smoot, who is a trailblazer and a pioneer and a legend in the industry. I expect most of you probably don't know how important BWXT is to nuclear technology, but they are on the cutting edge, on the forefront of things, and Sharon is a really big part of why they're there. And so I feel honored to be here. And I get to hear from somebody on a different side of the career spectrum. I graduated from Virginia Tech with my master's in nuclear engineering uh, last December. And so since then, I've been working at the Special Competitive Studies Project, where we have a commission on the scaling of fusion energy. Before I graduated from Virginia Tech, I went to UVA and got my BS in physics. I'm just going to run you through my career path a bit, say things that show some of my research experience, which is probably a little closer to your horizons right now. Um, and then leave you with a bit of advice. So I went to West Springfield High School up here in Northern Virginia for high school, and I've always loved the sort of mechanical side of things, and so I built some electric guitars, guitar pedals, just as a hobby for fun, and I loved my physics class, and so when I went on to college, I decided to be a physics major. Um, and then midway through my college experience, I started working at a laser lab on grounds. And so I had three main projects that I worked on there. One of them was, and this was the reason I signed on, was a lunar rover project. So the point of this project is you have a lunar station at the rim of a permanently shadowed crater. Inside that crater, a bunch of really cool materials to study. You have a rover inside. How do you charge it? We use a laser beam to track and remotely beam energy to this rover. Really cool project. Didn't end up getting too far, but a very neat thing. And then these images that you see here are micro lenses. So if you think of like an insect's compound eye, where you have a bunch of little lenses, that's essentially what I found ways to fabricate using lasers, using techniques with multiple different kinds of lasers to drill these indentations and then smooth them over to make a new kind of lens. And then I also did some materials testing for a novel silicon carbide material that the U.S. Navy wanted to test for hypersonic planes. So we were able to test it at like very high temperatures. And then after UVA, I moved to Virginia Tech, and got my master's degree in nuclear engineering. I decided to do a rotation and see what was going on in a couple different labs, which is a bit unusual for a master's degree, but I'm really glad I did it. And so I worked in three labs at Virginia Tech. The first two were in Blacksburg. So one was with Dr. Yang Liu, who does bubbly flow research. The other was with Dr. Jonathan Link, who has a mobile anti-neutrino detector that we parked outside of a nuclear power station and got data from that. And then I did my master's thesis work at the Virginia Tech Transport Theory Group under Dr. Aliweza Hagigat. Um, and this was a coding neutronic simulation lab. So I did that research in fission. Now I'm working in fusion. Just to be perfectly clear, so I'm just going to give a little intro on fusion and fission. Fission is the type of nuclear technology that we've had for 80 years-ish. And that is taking a big heavy atom like uranium, and then you split it, you get energy out of that splitting, use that energy to heat up some water and spin a turbine. That's how a nuclear reactor works. A fusion reactor is something that is a little bit on the horizon, but it is much closer than it's ever been before, and that is taking light elements, usually isotopes of hydrogen, and then combining them, which also releases some energy. And it's still probably going to be used to spin a turbine, but there are a couple companies with different approaches as to how to actually get energy or electricity out of it. So the first research I did at Virginia Tech was in bubbly flow. So in this lab setup, this matters in a nuclear reactor, right? You're heating water, you're boiling water, you're going to make some bubbles. You want to be able to control this because this is something that really affects how you can control your reactor. And so we had a clear chamber that we could pipe bubbles up from, and then we had three high-speed cameras that we would use to uh, look at the bubbles inside, to track them, to monitor them, to understand them and recreate them. What I did was I made like a digital twin of this, so we could see how effective these reconstruction algorithms were. And so generating my own bubbles, knowing where they are, and then generating like what these cameras are going to see because of that. And then this is a project I did not do much of any significant work on, but it is very cool. Jonathan Link's group, they had a mobile anti-neutrino detector. There's not really anything else like this in the world, certainly not with its level of accuracy. So it's just a bunch of plastic scintillators. So neutrinos are released, antineutrinos and neutrinos are released when you do nuclear fission reactions. And they pass through just about everything. So there are currently billions of antineutrinos passing through you right now. In your lifetime, maybe one of them, maybe two of them will make a collision somewhere. So very hard to detect. But if we had this anti-neutrino detector, we parked it right outside of a fission reactor, a power reactor called North Anna, which is about an hour and a half away from me right now, where I live in D.C. So it's if you go south. Um, and it was really effective at looking inside this reactor and seeing what its power level is. So the implication of this technology would be really useful for monitoring a country that you maybe don't trust with special nuclear material, to see that they're actually doing what they say they're doing. And you can do a sort of verification with your own device that you can just park outside of the building. And it doesn't have to be radioactive. It's really promising technology. Very cool stuff. And then here's what I spent the vast majority of my time in graduate school doing. So I was in the Virginia Tech Transport Theory group. And in this group, we developed a code called RAPID, Real-Time Analysis for In Situ Particle Detection, Particle In Situ Detection. And it can simulate the full core of a nuclear reactor. It can do it pinwise, and it can do it tens of thousands of times faster than the standard Monte Carlo codes with very similar fidelity. So it's difficult to overstate like how difficult computationally it is to do Monte Carlo, which has been the standard since the 1940s, of the best way to simulate nuclear reactors. To do rapid, you essentially run one Monte Carlo code as a pre-calculation, and then you can adjust it with little steps that take very, very little time. And it's clever in the assumptions that it makes. So the way that it will disregard some negligible values, the way that it takes advantage of symmetry, and reactors are usually pretty symmetrical. Um, and does it basically in one two-dimensional plane, and translate it effectively across the z-axis. And so as a result, it is really, really fast at what it does, and it can generate data sets that nobody else is able to generate. Um, and we did some validation of this. I went over to Slovenia in the fall of 2023 for a couple of months. And at this research reactor, I did some experiments. I learned how to operate a reactor, and we did validation that this code that we developed actually worked. Um, Fantastic experience. If you ever get the chance to go to Ljubljana, I fully recommend it. It's an amazing country with wonderful people. Okay. And then my specific research project that I worked on was to take a spent fuel cask. So these are the places that after our fuel is done in a reactor, we put it in a big concrete, steel, something like that cask, and just keep it there. And that's usually what happens with nuclear waste. And so the problem that I tested was, if we have a ring of detectors around the outside of this cask, can we see what the fuel looks like on the inside of the cask? Um, we had a nice little interface that Dr. Valerio Mascalino developed when he was a graduate student here, where I could pretty easily substitute in different burn-up values, so like how spent that fuel is. And then I tried it with a bunch of different machine learning methods. You can see here a decision tree. This is not a decision tree that I used because that would be too big to fit on the page. But four different methods: linear regression, k-nearest neighbors, decision trees, and random forest, to try and detect the location of differently burned fuel and to detect the amount of differently burned fuel. Did it in two problems. Um, it was pretty effective, much more effective at determining amount of burnup than location of burnup, but still statistically significant. So that was my graduate research. And now I am in the policy space. So I work for the Special Competitive Studies Project, which is a 501(c)(3) nonprofit that grew out of the National Security Council for AI, which was a government-run commission. Now we're a nonprofit privately funded by Dr. Eric Schmidt. Um, and it is a really amazing place to be. So we're the home of the Commission on the Scaling of Fusion Energy. Um, which is led by our CEO and two sitting U.S. senators, Marie Cantwell and Jim Risch, as well as a real who's who in the fusion industry. So we've got the CEO of the largest grid interconnection in the U.S., the CEOs of the two largest fusion companies in the U.S. We've got directors of two U.S. national labs, the most important two for fusion, as well as people from private capital, people from government. The former deputy secretary and undersecretary of energy are here as well. So it is absolutely the room that you want to be in to decide what we need to do to put fusion energy on the grid. We put out a preliminary report back in February with some of our initial recommendations for what we need to do to win the race against China to get fusion to the grid. Um, and we're going to put out our final report in October. In the meantime, I've been doing some research. So I've been writing a supply chain report that we're going to publish about the fusion supply chain. And it's going to be a detailed look at every significant component in this ecosystem, looking at every single company in the world and whether they use this component or not, and then what we should do to make sure that we have a supply for it in America. Also doing some research on like what China is doing in fusion and finding some novel locations that people haven't published locations for where they're building certain infrastructure projects. And we do a lot of work in the intersection of AI and fusion. And I'm doing some research for the Secretary of Energy right now. If I go back to this slide, that's that's me and the Secretary meeting about 2 weeks ago. Um, so that's what I do now. And I am really, really grateful to be working in the policy space because it allows me to have conversations and make a difference that I don't think I would be able to make until like 10 to 20 years into a pure research career, if that is the thing I went to. So, I mean, the fact that I'm already able to be doing something with the secretary, to be in conversations with Congress people, um, to determine what policy is going to be. It, Getting fusion on the grid is not just a technical problem. It is a problem of money and support from the government. And so the fact that I can be making things happen on this front really does fill me with a sense of purpose. Um, and I want to close with one piece of advice, and that is that I think the best skill that people in STEM can learn is communication. So I would say take a public speaking class, just practice every time you get the chance to. It is an act of empathy in understanding what your listener knows and meeting them where they're at. And it's something that if you are a really, really good communicator, that will separate you from everyone else in the STEM field. And it is something that is a skill that you can learn. And I'll provide an example here. That's not from my field. So Klaus Scholten was a biologist who proposed a theory back in 1978 for how birds are able to magnetorecept, so how they can tell the Earth's magnetic field for their migrations. And he published it in an obscure journal in a way that nobody who didn't have like a PhD level in both biology and quantum physics could understand. And no one paid attention because he didn't care about his audience. And as a result, it was only in 2000 when he got a graduate student who was good at communicating that it became a leading theory for how birds are able to magnetorecept. And so 22 years of research were basically lost because this guy didn't pay attention to communication. And so that's the one piece of advice I got. I am ready to move it over to questions. And thank you guys for your time.
Thank you so much, Caleb. That was a great presentation. Again, we love that you both, you, Caleb and Sharon, talked about those soft skills that are really important to support the progress of STEM. Like we said, communication, leadership skills, collaboration are all things that we all should be working on. I know some of you might be dreading that public speaking piece of, of your work, but we have to be able to communicate our ideas, which is so important. So thank you again for your presentations. We're going to go ahead and get started in questions. They came in some pretty early. So first question is, I think, a great one to start off with to cover the basics. Susanna's wondering, what is the difference between nuclear physics and nuclear engineering? Where I am in Lebanon, they don't have the nuclear engineering program, but they have nuclear physics. So I'm wondering what's the difference?
All right, Caleb, you're closer to having graduated from school than I am. I'm handing
Sure.
over to you.
Sure. All right. So I think nuclear physics is a bit more pure in terms of, just trying to understand exactly what's happening. Nuclear engineering is a fair bit more applied. So nuclear engineering is a lot more about power plants or in some specific cases weapons, but mostly about power plants. Um, and there are some things that are more or less important. So I'd say you can be a nuclear engineer without knowing what a quark is. You can be a nuclear physicist without knowing what a quark is. Um, but yeah, I mean it's mostly about the application. So you can be a nuclear engineer and specialize in like thermal hydraulics. And so your specialization is in water flow and you know that really, really well. Or it's in neutronics and you know neutronics really, really well. Nuclear physics is a lot more about understanding the atom itself.
Thank you for that. And then we have another question from Talon, who's a 10th rising 10th grader. So if you can go back in time, and I'd like to throw this out to both of you, if you can go back in time, what advice would you give to your younger self in high school when you were a student?
So for me, and so I was very shy in high school. And technically I'm still an introvert. Okay. You grow out of that as you progress and you get older. But for me, I would say don't hesitate to try different things. I stay very, very focused on science and math, and if it what didn't fit in that box, and music was a side thing that I did as well. So the guitar piece was fascinating because I say STEM plus arts because music is math to me. But I would tell my younger self, don't be afraid to broaden, explore, and do a variety of different things while I'm young, yeah, in grade school, as well as in college, exploring different classes for your electives. When you get into your career, exploring different jobs that you wouldn't have thought about being in your career path. So, eliminate that box you put yourself in and broaden yourself. It is something that you will greatly benefit from later in your years.
I think my answer is fairly similar. I wish I was a little more proactive in looking for opportunities. I waited until like before the start of my third year to start research. Um, it's something I could have done my first year of college, and I'd certainly have a bit wider breadth of experience, and I'd probably be doing some really cool research that I can bring home with me, and then just getting a wider taste of what it's like. Because going in, you only know what you've learned. And the only way to learn is by doing.
Awesome. Thank you so much for that. And, just a suggestion for you students too, we talk about broadening our horizons and trying new things, but also getting those new perspectives. So one component of that is looking at what research is out there and reading through some of those papers. So if you're trying to work on your technical writing skills, one piece of that is working on your technical reading skills and getting that language into your brain. So for example, we just had this past spring, Thanush Patlola, one of the finalists for Regeneron, the Star Science Talent Search, and he did his paper on nuclear theory and that sort of thing. So that might be a research project that you look into as an example to get your toes in the water when it comes to nuclear engineering. So just a suggestion. All right. So going into those softer skills, what does communication mean to you and how do you develop those skills?
Sure, I'll go ahead. So I mean, I think fundamentally, it is the act of considering where your audience is and delivering your message in a way that is most effective to them. And so uh, I assume if you've got any interesting technical thing that you want to talk about, you're probably going to deliver a different message to your grandmother as you would to a professor in that topic or an adjacent topic, right? And so it is understanding where your audience is at is the important thing. How do you get better at it? The best way is to be explaining all the time, in a non-overbearing way, but to explain what you can to different kinds of audiences. Um, when when I am delivering a message to like a member of Congress, like it is very important for me to be able to show why is this important? Why do you care about this thing that I want you to care about? And it's very often people without any sort of technical experience. And so speaking in analogies can be a really effective way that can be more effective than just a number with some unit that they don't understand. So meet them where they're at is a big part of it.
I agree with all of that. So the only thing I will add without repeating what Caleb said is I in my leadership courses that I've taught, I always started off with communication is the hardest thing. You think you're saying one thing and communicating that, and what your audience is hearing may be something completely different. So the storytelling technique, things like that you learn. There are also courses you can take and things you can do to enhance your communication skill, but it is hard. It will always be hard. I speak because I spent so many years in the Navy in acronyms and I don't even know it. So I talk to people who have nothing to do with what my career is about to see if they understand anything I'm saying to help me talk to my audience. When you're in a room, you're an engineer and you're working on a program, and you're in a room full of engineers, you're all vibing together. You're all speaking the same language. Everybody's head is nodding up and down. Most of your most important speaking opportunities when you are truly trying to communicate will be people outside of that community. So just practice and kind of think to yourself, speak English. Don't use a lot of technical terms, things of that nature, and just, practice. It's hard and it will continue to be hard as you progress through school and college and into your career, but it is one of the most important skills you need to learn.
And just
That and
building
writing.
Absolutely. And building on to that, I think a lot of our students are not aware that, yes, you can be with your same group of peers over and over again, but then does that drive progress if you're just having the same echo chamber conversations over and over again? By expanding your audience and speaking to anybody about what you're passionate about, you can drive innovation and get more inspiration and ideas. So that's very important. Thank you for bringing that up. Let's see. Um, just to build on that question, because I know I've seen it's come up a couple of times in here. So we talked about communication skills. What about leadership skills, especially at like the high school level? Because we have leadership courses, minors, majors in college. So what about in high school?
You want me to go back and try to remember everything. So I'll explain it this way. I'll tell you things that I did to my son, who is now 30 years old, but I remember more about what I did to him in high school than what I did to myself. Um, Anytime you have an opportunity in a club, be an officer. Okay, don't be afraid to step into those roles because now is the time to practice those skill sets before it has consequences later. So, and band, be the section leader in your language club or your math club, be the chair, be the president, be in a leadership position, honing those skills. In any opportunity you want, a class president, volunteer in a class to organize something, be that person, kind of step out of your comfort zone or make yourself be uncomfortable. You know, you've heard the term get comfortable with being uncomfortable. that that the earlier you start pushing yourself to do that, the better. And then you will hone those leadership skills much earlier than I did. And I wish I had worked on that earlier.
Uh, Sharon, that was a fantastic answer. Um, Something I'll add is kind of going back to what I said about communication, is about understanding the people around you and what their strengths are, what their weaknesses are, and if you have a chance, put them in a place to best succeed. I've got a model that I really like called the competing values model, that takes four different types or archetypes of people, and obviously no one is exactly one thing. But saying, what does this person value? What do they care about? And then put them in a position that makes it happen. You know, if you have somebody who cares about doing something right, they are going to be fantastic at finishing touches, at making processes that last, making a product that really, really works. But they are not going to be good at driving out on the initial cutting edge of something really experimental and new and creative, generally speaking.
Awesome. Thank you so much. So now shifting gears into that research space, I think Caleb will have you start with this question since you're fresh off of your research. So where exactly do you start with research? How do you identify a topic or, find a investigator that is studying something that is of interest to you?
Yeah. So I now at the high school level, it'll certainly be different. At the college level, there will be lists you can go to in your department of all of their faculty. And then all of those lists will contain a description of their research. And this is something I didn't go through for too long. I should have done this first thing before I started at college. But find that faculty, see what seems interesting, and then just shoot them an email. And then let them know who you are. And you might feel like, okay, I'm gonna be a freshman in college. They're not gonna want me. They might. Send them an email. The email will be right there. And so they will pick a project that is appropriate for you. And you can say what you find most interesting. You can take a tour of a couple different labs, and see what strikes your fancy in that way. But that information is there. Now for at the high school level, I don't know nearly as much, but I bet there are other people on this call who do.
That would not be me. So I'll talk from an industry standpoint. Most of either the labs of the government or the research in industry, it starts with solving a problem. Okay. So you have a problem. So fission in it itself is not a problem, but it does produce some byproducts that are difficult to deal with given the half-life of some of those, some of the waste generated from the generation of that energy, where fusion solves that problem. And it provides this almost endless source of energy. And one of the problems that we have today is we are a mass consumer of energy. Think about it. Data processing by itself. AI is going to be an energy draw. Electric vehicles. I mean, just think of everything that we have to power up or draw from energy. So the evolution of that technology is coming from that problem statement of how do we have enough energy to power up all of the other things that are coming, things that we have now and things that are under development. So I say, from an industry standpoint, is here's a problem. We need to go faster. It needs to be more sustainable. We need to, whatever the need is, we then launch research on how do we develop something better than what we have today, or something that solves a problem that we see today.
Awesome. Thanks so much. Love to hear it from both sides of the aisle there. So I just had a student that from the Lyceums mentorship program have success at the high school level when it comes to their research. So just to give you all a little bit of background of what you might be able to do at the high school level, what my student did is she emailed a few professors and asked if there were any virtual options that she might be able to get involved with. So it would be that, data analysis or any coding that she might be able to do for their research as just an aid, just to gain some experience and explain why she was interested in that specific research. Again, you don't just ask for a research position, you explain why you're interested and why it's valuable to you and to the world as a whole. So you make it personal and you actually show your dedication to the craft. So that's an example of something you might be able to do at the high school level, something virtual or asynchronous to what the research is doing. So thank you so much for that. And Sharon, you brought up an excellent point about what we know about how nuclear power is communicated. And there's a question in here from Isla that I think can connect to that. So I want us to move over to that. So it says, I know safety can be a concern in nuclear energy, although it's actually more safe than a lot of us expect. So what's one of the major challenges engineers face when developing safe nuclear power, as well as communicating its safety and its benefits to the public, when many people are hesitant about it?
So I'll start and hand over to Caleb because he's closer to the fusion technology, which solves all kinds of stuff. It's, the first problem or challenge is when you say nuclear power, people default to weapons and it becomes scary. Nuclear energy, nuclear power is inherently safe. It's clean energy. It is well developed through decades of industry, federal government partnerships. It is built in a nuclear power plant that has inherent safety mechanisms and control systems in it to prevent the bad things from happening. And we in this world and in my lifetime have had the Fukushima plants, the 3 Mile Island there. I mean, you can go online and see the things that went badly over a series of events, but safety is built into commercial nuclear power, even the Navy's nuclear power, even more so in the Navy's nuclear power program, to prevent impacts to the environment and to people. Everything is measured, environmental impact, exposure to people. It's well controlled, well documented. I felt growing up in a program with nuclear power very safe personally, and I felt like the environment around me was well protected. And with all of that, all of us that were in that program were held responsible for the education and training, which is largely focused on safety. And I can't say enough about it, but that's the fission side of the business. The fusion side of the business goes that much further and solves a lot of those things that people worry about that I would say they don't need to worry about.
Yeah, the safety issue is much more of a PR one than of a technological one at this point in time. And American reactors have pretty much always been pretty well built and well regulated. So something like Chernobyl could never have happened with any American commercial power designs. But also part of it is radiation is a difficult thing to understand. And I don't blame the average person for not understanding it and for being afraid of the concept of radiation, but it is all around us all the time anyway. Yet if you eat a banana or if you are next to another person, when I moved to Slovenia and I operated a nuclear reactor, the most radiation I received was on taking the flight over there. Right. That was the biggest dosage. Um, and so I mean it's a PR thing and it's something that we certainly need to get out ahead of. And I think these new frontiers can be good if we can anticipate the messaging and set the tone right. And this can be true with SMRs, which work well enough as a catchphrase of just calling it an SMR and not calling it a small nuclear reactor. Um, and fusion as well does have some inherent advantages. So you don't need clever engineering to shut down a fusion chain reaction because it's really, really difficult to get to that fusion reaction in the first place. Whereas like a fission reaction, that's something that has happened naturally on Earth, right? There was a natural nuclear reactor a couple of billion years ago. But you don't have those runaway chain reactions as a potential problem, and a very different level of radiation. So no millions of years of nuclear waste as a problem with fusion, which is not going to create any long-lived waste like that. Um, so some differences that are helpful in the messaging, but as far as power sources that we currently have on the grid, nuclear is the best one. Nuclear fission is the best one.
Can
Nuclear
I jump
waste.
on something Caleb
Mhm.
said? It's a funny story, and it goes back to communication where I had an audience of non-technical personnel. I own radiation safety program for the Navy, and I was trying to explain radiation safety and exposure, and I used the banana as an example. Everyday thing, granite in your house, natural stones, elevation. If you're at the higher elevations in Colorado, you get more exposure than you get from. If you're flying across the country, you get more radiation exposure. And then I got to the banana, and the gentleman that was sitting across from me looked shocked. He says, "So I have to stop eating bananas?" No. I said, I did a poor job of communicating that. It is that we have naturally occurring radiation and radiation exposure around us all the time. And we put ourselves, whether we're in the sun and on flying from coast to coast, in circumstances where that exposure gets greater. It's only when you talk about it as nuclear power that our brains shut off what we naturally get exposed to something that sounds scary, and it's not. It's actually safer than and more controlled than the natural occurring. But communication is the hardest part of that.
Thank you so much, the both of you, for those very thoughtful answers. And I think it, like we said, it all comes back down to how do we communicate the messaging that affects the policy space and and the technical space in order to make everybody feel more comfortable with what is a really great clean energy option, especially with the advent of AI, machine learning, and the data resources that we need for supporting that new technology. So again, thank you both for joining us. We're at about time, so we need to move on to our thank yous. I want to set a thank you to our audience, our first group of the fall season, to the new friends and our old friends. Thank you so much for participating today. Lovely questions. Everybody was very active. It was great to see, and I hope to see you at our next session. So before we move on, I'd like to thank our sponsors. They are who allow us to keep this programming cost free. I'd like to especially thank the Claude Moore Charitable Foundation. Um, we love our sponsors. They keep us together on this whole thing. So thank you, thank you. Again, thank you to our speakers, Caleb, Sharon. It was a fabulous presentation, and thank you to my audience. Our next session is Opportunities in Research. We're going to be joined by two students from Rutgers University who are participating in research labs currently at their school in the microbiology and health space. So if you are interested in health sciences, and potential MD, studying for MCATs, this will be a great session to attend. I also encourage you, please fill out the post-webinar survey by either going through the QR code or filling out the 4-question survey that will pop up at the end of the Zoom session. Your data is useful for me to give you awesome programming like we just had today, and also it serves as your attendance check. So if you fill out the survey QR code, if you watch asynchronously or right now, it serves as your attendance so that I can keep an eye on how you participate, what you're doing, and it opens up opportunities for suggestions of participation in the mentorship program and other things. So please fill out the survey and register for our next session. Thank you all.